All right. Cool. Well, welcome everybody to spring quarter, and welcome to Engineering 250. So, if you had a break, hope you had a good one. I think it was way too short, personally. All right. Well, hopefully everybody who's not here will be coming in. We're missing about a quarter of the class, but we're going to go ahead and get started anyway. We've got 10 weeks in this term. We meet for a little under 2 hours a day, 2 days a week. That's under 40 hours. That's not a lot of time. So we're going to jump into things right now. I'm going to talk a little bit about syllabus type stuff, but mostly we're going to spend today actually going over some digital logic and talking about your first lab, which is due on Friday. So we're gonna kind of jump right into that. So again, welcome. This is Engineering 250. So this is in most ways a sequel to Engineering Computer Science 120, which is the intro ECS lab. And that course is a number of things. It's digital logic, it's analog circuitry, it's electricity, power, voltage, current, resistance, all of these concepts. It's also, some engineering math, some things like ethics, creative problem solving, and so on and so forth. This course takes one of those areas from ECS 120 and just really drills down into that. And that's the area of digital logic. And so there's one unit in 120 where you work with logic gates, you make truth tables, you talk about logical operations like and, or, not, and you design a circuit, usually like, an aircraft landing circuit or something like that. That's what we're doing in this course. We're just taking that aspect of electrical engineering, digital logic, and just extending that out. And for many people, this course becomes the foundation for what else they do in computer science or in electrical engineering. It's a kind of fundamental course, not because you're going to be designing circuits on proto boards with integrated circuits necessarily if you're a programmer, but the problem solving you do in this course translates really well to problem solving in computer science in general or in electrical engineering. So it's a pretty key course in a lot of ways. Let me go ahead and hop onto Canvas and just do a well, I don't need to go onto Canvas actually. If you go onto Canvas, there's a few pieces of information to pay attention to. So let me hop in here. So the main thing to start with is just the syllabus and additional course policies. Everybody who's here has the Zoom info, so you're all set with that. Your coffee's ready to go.
Awesome.
Okay. But I'm not going to take these through the web. I'm just going to pull these off directly. Alright, so first course in digital design is 2-course sequence. The second one is Engineering 270 microprocessors, which we will hopefully be in person for if you're taking that with me in the summer. So 250, we meet daily, 8 o'clock to 10 o'clock. This is a remote class. It's not online in the traditional sense where you can come to whatever lectures you want and read the material at your own pace. This is run like an in-person class, except the modality is remote. So we meet every day, Monday, Wednesday, 8 o'clock. We'll go till 9:50 a.m. My name's Nick Macias. I've been teaching 250 here for, I think it's almost a decade now, so I'm pretty familiar with the material at this point. We've updated the course over time. It's never the same course twice, but a lot of it is unchanged from offering to offering, and the subject of digital logic is in some ways very old. A lot of what we build on is Boolean algebra, Boolean logic, which is, almost 200 years old as a subject. But there is a official textbook for the course, which is a free download, so you can grab that from this link. Izad, the teacher of the other section, one of the teachers of the other sections, wrote this book for the course. There's my email address. You can always try to reach me through email, and I'll usually get back to you within a day. I also have office hours scheduled, and you can find those hours on this website. And that lists office hours for all of the engineering computer science faculty. So you can find my hours as well as Izad, Carol, and Tina, Jesse, and so on. And there's Zoom info on there and so on and so forth. So I have 5 office hours a week, which is for all of my classes plus for advising, because I work as a faculty advisor as well. There's also 3 lab hours a week just for this class, and that'll be Wednesday afternoons, evenings, so we'll talk about that in a minute. But those are the best time if you want a good chance of being able to get large chunks of my time to help with questions about the labs. Lab hours are your best bet, but you can also come to regular office hours. But I don't list my lab hours on this site, so that should just say for office hours. I'll let you read the course outcomes and think about those, but these are the things that we intend you to understand after you leave the course. Tentative outline is roughly how I'm planning to lay things out, but that usually changes over time. Grading, so you have 4 components to your grade: labs, homework, and then 2 exams. Labs will be pretty much weekly, starting with your first lab, which you can begin today and turn in on Friday. That's a quarter of your grade. Homeworks will come in once a week, but there will be no homework due this week. And that'll be 20%. And labs and homework are a really great way to understand what might be on the exams and to practice for the exams. So in addition to being a direct large component of your grade, they also help you know if you're ready for the exams, which are 25 and 30% of your grade for the midterm and final. And I will let you read through the rest of this. Chances are you've been here at Clark for at least 3 quarters now, possibly more than that. But look through this, make sure you understand the support services available at Clark, the accommodations, student support, and so on and so forth, as well as the college-wide policies regarding non-discrimination, Title IX, and so on and so forth. And I think that's all I want to say about the syllabus right now. In general, I like to keep these classes as interactive as possible. And so I'll tell you what I tell my classes when we're in person, right? If you have questions, just go ahead and either put a message in the chat window or unmute your microphone and just go ahead and ask. I can't see if people aren't using their cameras, and it looks like no one is using their camera. I can't see if people, are looking confused or, whispering to a neighbor to try to get clarification on something. So I have no way of knowing if what I'm saying is making sense or if people are completely lost. So you gotta take the initiative to sort of step up and say, hey, wait a minute, what is this you're talking about? Or what did you mean by such and such? Or that doesn't make any sense, or whatever. And the more interactive you make this, the better it's going to be. It's a 2-hour meeting. That's a really long time to just sort of listen to me talk, right? So ask questions, think about stuff as we're going through it, and so on and so forth. All right, additional course policies. So there's my office hours, including Zoom info. We meet Monday, Wednesday, 8 to 10. Lab hours, so Wednesday evenings 5 to 8. All right, so those are 3 hours a week, which I'm dedicating just to this class. So I'm not advertising them on ENGR250.com. You won't be competing with students from other classes or students looking for advising help. Those are just for this class. You can work on the labs anytime that you want, but I strongly recommend, working on them as soon as we go over them, which will typically be Monday. And then you can ask for more help in class on Wednesday, and then if you're still stuck and you can't finish them by Wednesday afternoon, you can come to office hours and ask questions there. But don't plan on starting the labs Wednesday evening in office hours, right? Because you got 20 people you're going to be competing with. And the time, if you're totally lost, if you're completely unsure how to begin something with a lab, ask about it in class. All right, cool. We've got everybody in here now. Well, we had everybody in here now. All right, again, it's a remote class. Sorry, say again?
Sorry, I had to reconnect to my computer because
okay.
I was on my phone and now I'm on my laptop.
Okay, cool. All right, class is remote, so we have fixed meeting times. I will note attendance, but I'm not counting attendance in your grade at this point. That could change down the road. Nonetheless, I expect people to come to every class and to try to be here as close to on time and stay for the whole class, and to try to stay present during class. Don't just turn on Zoom and then go off and work on something else, and wait to hear your name or wait to hear the word exam or test or something like that, right? If you can think of this as an in-person class, right? You come in and the door is closed at 8, and you're pretty much here unless you need to get up for a few minutes or something. And just kind of resign yourself to, that's what this chunk of time is for. If you have, the luxury of being able to do that, right? You will get a lot more out of this if you really kind of dedicate this time to working on this course. The lectures are recorded, and they are posted on YouTube, and they're tagged with timestamps. But you can't really succeed in the course just by watching the lectures, right? Number one, nobody's going to watch 4 hours of YouTube lectures on Engineering 250 every week. It just doesn't happen. And trying to hunt and peck through the lectures to answer homework questions or things that I say might be on the test is not really a good strategy. Right, that's like having a textbook and browsing it to try to find answers. You can get away with that for a while. I got away with that for a while in school, but for courses that are sort of foundational that you're really going to build on in coming years, you really want something better than a sort of passing understanding of the key concepts. You really want to understand this material. So plan on coming to class and trying to stay present and participating as much as you can. Along that line, right, I don't require people to use their cameras, but you are welcome and encouraged to use your cameras. If you can see other people taking the class while you are, it's going to feel less like, you're sitting in a room staring at a computer all day, and, a little bit more like you're in a classroom situation, like you're learning a subject with other people. So I encourage people to use their cameras as much as you're comfortable with. I record the lectures, and basically everything that you see on my shared screen, that's what's going into the lecture. Everything that you hear on the microphone, that's what's going into the lecture recording. So I don't record the chat window, I don't record the list of participants, and so on. It's basically what you're seeing here. Given that, if you're uncomfortable with this, let me know. If you don't want your voice to be recorded, can go ahead and let me know that, right? And either talk to me through chat, or send a chat message and say, can you not record my talking because I want to ask a question or something like that. So we'll figure that out. And yeah, so some people are saying if they turn their cam on, it makes the Zoom stream choppy, and that's definitely an issue sometimes. So you can experiment with that. All right, so again, I won't be counting attendance. I will be noting attendance. And generally, if you don't come to class, your grade will suffer. Right? If you miss 3 classes, you'll probably drop a letter grade. That's not policy. That's just an observed reality. There's so much material we're going to go through, and we're going to go through it so quickly, and you need to be able to ask questions about things that are confusing while we're going through it. If we go through a subject and there's no questions, we're going to start building on that subject right away. And if you miss one class, we might have, 4 or 5 different things that we built on top of other things. And the next class you come to, we're talking in a totally different language, and nothing is making sense, and you can't make anything out of what we're discussing, and you're effectively missing that class. And now you've missed a week of material. That's 10% of the course, and you got to find a way to catch up on that, and then, continue from there. So come to class. All right, lab assignments, there's links to those in Canvas. We'll talk about lab reports in the second half of this morning when we go through the first lab. Lab reports are different from homework. They have different requirements for what you turn in and so on. Individual work, make sure that all the work you do in this course is your own. There are so many online resources available right now. Some of the resources are very good. Some of them are very poor. If you Google a homework question, if you Google a lab question, right, you will find tons of answers coming back to you from places like Chegg and Course Hero and so on. Some of these answers are not bad in quality, but taking an answer from online and turning that in does nothing for your learning. And it also puts you at extreme risk of being called out for plagiarism. And if that happens, that's a whole experience you don't want to go through. So my advice is try to avoid online research and ask questions in class. That's your first bet, and you're never going to get in trouble for asking questions in class, and you're never going to get in trouble for asking questions in office hour, right? Asking Google for help, that's where you start to get into trouble. And even if you see an answer and you try to modify it to put it in your own terms, so that it becomes more your own work, it's usually pretty easy to say, hey, this came from such and such source. And if that happens, right, it's a 0 first time. If it happens a second time, you're out of the course, and you're probably in front of the honor board and potentially out of the whole program. If it happens at a university, it's usually, you're done with the course on the first offense. So just stay clear of that, and if you have any questions, just ask. Is it okay if I do such and such? I saw this online. Can I go ahead and use that in my report? That kind of thing. Late work has to be turned in on time and in the required form. So your homework, your labs, they get uploaded through Canvas, right? We don't really have a choice right now because we're not in person, we're remote, but material has to be turned in on time. And it's an automatic 0 otherwise, except for labs. Okay, labs, you're required to turn in all the labs in order to pass the course. So I'll take late labs, but they cost you 20 points a day. So if your lab is 5 days late, it's a 0, right? So plan on taking the deadlines as extremely serious, and turn in your labs on time. And the last thing is, when you get a graded assignment back, double check Canvas, right? Make sure that the grade that's in Canvas is accurately reflected, and if it's not, send me a note right then and say, hey, you gave me 20 out of 20 in my homework, but Canvas says a 0, right? Because I've got close to 100 students this quarter. I make mistakes sometimes, so double check your grades as they come in, instead of at the end of the quarter, like, hey, 8 weeks ago I thought I got a 20 and you gave me a 19. That's harder to do anything about. All right. Questions on any of the syllabus related information? So we are meeting remotely, probably for the entire quarter. I had to switch the modality of the class from online to remote in order to start remotely, and my personal feeling was it was safer to either have everybody wear masks or just start off remote for the first 2 weeks. But I think that means we're remote for the entire quarter now. So we're gonna do the best we can with Zoom, but hopefully we will keep it as close to a classroom experience as we can. So lectures are recorded, and I post them usually a few hours after class. And there's a YouTube channel, CSE 220, 2021, 2022. This has lectures from both my computer science courses and engineering courses. So ENGR250 will be on here, and you gotta get good at searching because it's everything since fall. There's also a topic list, and if you click through to that, this is just a plain text web page, so you can search for stuff in here. But every topic that we go through should be in here with a link to the notion to the class, the date, and then the timestamp. And if you go to that video, those lectures are clickable, time-stamped. There's a link to some other videos you may find useful related to using some of the equipment involved in this course, oscilloscopes, things like that. More of an aid when we're in person than remote, but still useful for the concepts. Along with a review of using a protoboard. We're doing our labs using tinkercad, so you've probably done this in 120. And so we'll be using, a software package to pretend that we're using protoboards, putting components in, taking test measurements, and so on and so forth. Alright, homework will be assigned each week and due on Wednesday, so we'll talk about homework 1 this coming Wednesday, and then you'll have a week to do it. Homework is due at 8 in the morning, so right at the start of class. So don't think that it's due at midnight and then Wednesday comes and you haven't turned it in. If it's not turned in by the deadline, it's 0 points. Labs, first lab will be due this Friday, again at 8 o'clock. And then midterm exam and final exam. That's pretty much all I've got for administrative stuff. Uh, 8 a.m. Friday. Well, let me double check here. Oh, that's weird. Okay, no, homeworks are due at 3. I gave you some time. All right, so okay. All right. Check Canvas for what time it's due. So I think I set the homeworks to be at 3 p.m. I thought it was 8 in the morning, but whatever Canvas says, we'll go with that. And those are generally due Wednesdays, except the last one will be due on Monday so that we can talk about it that last Wednesday. And then labs are due at noon on Fridays. And that I think I set up consistently. Alright, so homework's on Wednesdays, labs on Fridays. Alright, other questions on any of that? Alright, well, let's get down to the subject matter then. So, digital logic. What does digital mean? We see this word thrown around. It's a marketing term for sure, right? Digital sound processing, digital radio, digital technology, right? It's a buzzword. What does digital mean? If you had to explain to someone what that term is, what kinds of things would come to mind? Let's just toss out some ideas.
Runs on some form of electricity.
Runs on some form of electricity. That makes sense. Digits, numbers, not physical. Okay, good. Uses digits, typically 1 and 0. Okay. 1 and 0. So, that's an interesting concept. So when we learn math in school, when we learn to add and to calculate areas and things like that, we deal with numbers, right? Like, 12 or 3.14159 or, 10,000 or negative 15. And when we talk about digital, in some sense, we talk about a much smaller set of numbers. We talk about a 1 and a 0. Someone said something analog that has been converted to digital. So here's another question. What do we mean by analog as opposed to digital? And now we're getting deeper into marketing territory. Manual, good. The sound you hear in the world, a bird tweeting. Yeah, I've got a bird that tweets at 6 in the morning. Yeah, a sound that you hear in the world is analog. And this sounds a little bit like what somebody said about not physical for digital. Let's keep expanding that idea because I think that's a pretty key notion. Do we have digital sounds? A bird tweeting is an analog sound. Are there digital sounds or non-analog?
There's digital feedback.
There's digital feedback. What does a sound look like? Is there a way to visualize it? We know what it sounds like because we have ears. Looks like a wave. Waves, yeah. If we wanted to visualize a sound, we could draw something like this. And what is this thing? Well, it's a graph. And most of these graphs we're going to see in this course, we usually think of time as moving along one axis, and this line is showing something that changes as time changes. And this thing that's being shown could be a number of different things. It could just be a mathematical function. But it could be that this is a measure of air pressure. This could be the air pressure inside my ear as I'm observing a sound that's being made by a bird at 6 in the morning, right? And the pressure is, goes from nothing to some positive pressure, which means, my eardrum is moving inward, closer to my brain, and then the pressure drops a little and raises again, and then it drops quite a bit, goes back to 0, and then goes negative, which means my eardrum is moving away from its rest position, farther out of my head, and it wiggles around a little and then comes back. And what's happening here, my eardrum is vibrating, right? Positive pressure, negative pressure, positive pressure, negative pressure. And this could be a graph of how much that membrane in my ear has moved. Or, as that moves, all these mechanisms in your ear, the little bones and all that kind of stuff, eventually generate electrical signals that go into your brain. And electrical signals, how do we measure? What are some of the things we can measure about an electrical signal? What are some of the quantities or characteristics associated with an electrical signal? Some of the terms from 120. Ohms. So ohms would be...
Amps and volts.
Ohms would be resistance. I heard volts. What was the other one?
Amperages.
Amperages. Right? Those are really the three main ones. Yeah, voltage, current, and resistance. So this is voltage. Amps are a measure of current, and ohms are a measure of resistance. And we're mostly going to think about voltage in this course. If we know voltage and resistance, we can get current, right? That's what Ohm's law tells us. We're not going to really worry too much about Ohm's law here. We're going to mostly think about voltage. And this could be the voltage, traveling along some pathway in my brain. Or if we have a speaker, you have wires coming from, some sort of amplifier to your speaker. This could be the voltage that you would measure across the two wires going into your speaker. And the waveform you got from that would look very much like the waveform you got when you looked at the movement of an eardrum or the pressure wave going through the air and so on. But the detail of all of this is that this is an analog signal. If you were to try to read, the numbers, let's say that this is, 0.2 volts and this is negative 0.2 volts. I could say, right here at this time, my voltage was 0.083 volts. And at this point right here, my voltage was 0.212 volts. And at this point right here, it was, 0.191 volts. Or 191 millivolts. And at each point in time, we can identify what the voltage was. So the things that make this an analog signal are the fact that these voltage readings are what we call real numbers. They're numbers like this, or this, or this. And that's the world we live in. That's the way the universe works, right? That's what our signals that we might look at actually look like. But that's a hard world to work with. So how many people here enjoy doing KVL, KCL? With the multiple equations and the currents that add up and all that kind of stuff. Right? Most people are glad when I say we're not going to do any KVL, KCL in this course. It's fun once you know how to do it. It's kind of a cool procedure to go through and get the answers out. But it's a lot of work, right? And dealing with these sort of real values of voltages and currents and stuff, it's hard for us. It's really hard for a computer. And so as computers became more ubiquitous, and we tried to do more and more things with computers, we found that we could take a waveform like this, and we could approximate it. And we approximate it by saying, hey, we're only concerned with two things, a 0 and a 1. And so we split our range of possible values into two buckets. And basically we're going to say everything down here is a 0, everything up here is a 1. And so what's our voltage right here? It's 1. What's our voltage right here? It's 1. What's our voltage right here? It's 1. And so this waveform looks like this. And right here, as soon as we get a little bit negative, what's our voltage? It's a 0. And so our waveform looks like this. And then here it's a 1. And here it's a 0. And here it's a 1. And there's our digital version of this analog waveform.
I have a question.
Mm-hmm.
So I know this is not how sound waves work, but on your graph, you have kind of the waves doubling back, kind of on that second bridge. It doubles back.
Yeah.
Right there. Would that be just?
That was a
would we
typo.
not see that, or okay?
Yeah, that was just badly drawn. I tried to hide that by making this go back a little bit, but I didn't make it. Yeah, so these things can be thought of as functions in a mathematical sense. At any point, there's only one value for the waveform. So we can approximate this with something that has only two values, a 0 or a 1. And this darker line that we've got drawn here, this would be the digital version of this analog signal. And we'll talk about digitizing separately. We'll talk about it a little more in this course, and in Engineering 270, the sequel, we'll talk more about this idea of turning an analog waveform into a digital. And it's an approximation, and this is what your CD does. This is what digital headphones do, right? They give you an approximation. It's a better approximation than this, but it's still an approximation. This is why people who like good sound quality still use analog circuitry. They'll use tube amplifiers. They'll play records on vinyl instead of a CD, and so on and so forth. So we'll dig into that down the road, but digital, right? So for us, digital, two values typically, right? Which we think of as 0 and 1. And so in some sense, this makes life easier, right? We don't have to worry about, numbers like this. We don't have to worry about, what is this times that. All these calculations that we did in 120 when you have to find power by multiplying voltage and current and so on. Well, in a digital world, things are pretty simple, right? Every value that we deal with is basically a 0 or a 1. And this is nice because when we try to build circuits that work with, values, we've only got to deal with two values, just 0s and 1s. So suppose I wanted to make a multiplication circuit, right? And suppose I have two numbers, A and B, and I want to just multiply them. Well, since A is either a 0 or a 1 and B is either a 0 or a 1, there's only 4 situations for which I need to know how to multiply A and B. If they're both 0, or if either one is 0, then A times B is 0. And if they're both 1, A times B is 1. And so, when you're in school, you learn to multiply numbers. Well, you start with a multiplication table, and it's, typically 12 by 12 or 15 by 15 or something, and it's got a few hundred entries in it that tell you how to multiply these smaller numbers, and then you learn how to do, add and shift and pencil and paper, multiplication and so on. Well, if my numbers are just 0 and 1, if those are the only numbers I know about, there's my whole multiplication table. It's just 4 lines. So the kinds of things we can do with these binary values are much fewer and much simpler. That works for us. The downside of that is that to do complex things, we need to do a lot more work. If we wanted to multiply large numbers and all we have in our world is a 0 and a 1, we got to do something to be able to represent large numbers with zeros and ones. So our operations get smaller, but we have to do more of those operations. All right, so one term we'll toss around a lot is Boolean. And so Boolean logic, Boolean algebra, Boolean number systems, we're thinking about these systems where we have, just two things, 0 and 1. And we use 0, 1 because, we're techie people, we're math friendly and so on and so forth, but there's nothing magic about the digit 0 and the digit 1. And so sometimes we think of our Boolean world as comprised of two things which we can call false and true. Or we can think of these as no and yes. Or we can think of these as off and on. Or we could think of it as down and up. And it doesn't really matter what we call these things. We'll most often think about these as 0, 1 or false and true. But really, any way that we choose to split things into two buckets, we can use those two types of buckets to represent our two possible values for things in this Boolean or this digital world. And just to keep things interesting, some people will use a 0 to represent true and a 1 to represent false. This is called negative logic. And it's a very popular thing when you get into more advanced systems, like when you start implementing memory systems, for example. Sometimes a 0 will be considered true, or a true will be considered a 0. It's pretty much arbitrary. But this is the convention we'll mostly start with. We'll get to these later. All right, so here's a question. If you've got, real numbers, if you've got pi and -15 and so on, you can add, subtract, multiply, divide, take square roots, take logarithms, exponents. You can do all kinds of things, right? If your whole world consists of just a 0 and a 1, what kinds of operations can you do? So you have, a variable x, which is a 0 or a 1. Is there anything interesting you can do to x to get a different number? Does it make sense to talk about operations on Boolean?
Pass it in a function.
Pass it in a function. What could that function do, for example? So yeah, let's think about two variables. Let's have an x and a y. And if you have two variables, there's 4 possibilities. Both of those could be 0, both of them could be 1, or one could be 0 and the other could be 1. So we could do multiplication. We could do x times y. Somebody said that in chat. And so, you know, anything times 0 is a 0. A 1 times a 1 is a 1. Division, yeah, division would be tricky because we don't like to divide by 0. What else could we do? So someone said OR gate. What does that mean to you? What could we OR? Addition. So addition, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. This one gets tricky though. 1 plus 1 would be 2, and 2 is not a Boolean number. Right? My whole universe consists of just zeros and ones. So I'm just going to put a 1 in here, and I'm going to say I'm just weird that way. And I'm going to change the name of this, so instead of saying addition, I'm going to put in what someone said in chat. I'm going to say this is an OR operation. And the way I'm thinking of it as an OR is I'm thinking of 0 is false and 1 is true. Right? So I'm sticking with kind of this first alternative to 0 and 1, false and true. And I'm thinking logically, just, you know, plain old logical reasoning. If I know that something is true and something else is false, if I now ask the question, is this true or is this true? The answer is yes. Right? So X may be the question, is today Monday? And Y might be the question, am I eating birthday cake for breakfast? Right? Well, X is true and Y is false. But the OR would be the question, is today Monday or am I eating birthday cake for breakfast? Well, the answer to that is true, because today is Monday. And if both things are true, is today Monday and is it morning? Well, if this says, is it Monday or is it morning? Yes, that's definitely true, if I know that both of these are true. So this looks like an addition, except maybe for this last row. We're going to think of this as an OR operation. And this thing, which looks exactly like multiplication, we're going to think of that as an AND. And the AND operation says, is this true and is that true? If the answer is yes, then the AND is also true. Let's see, a subtraction would be interesting. And it's tricky again because to do any of these operations we need to get a 0 or a 1. So we could do 0 minus 0 would be 0, but 0 minus 1 would be negative 1, and I'm not sure what we get for that. We probably, I mean, we could decide that's a 1 or that's a 0, and then 1 minus 1 would be a 0. And so we'd get something, depending on how we define that. Or 0 minus 0 equals 1. Okay, so let's see what this does. 0 minus 0 equals 1. 0 minus 1 is equal to 0. 1 minus 1 is equal to 0. And 1 minus 0 is presumably 1. And this is a perfectly valid function that we can define on two variables, x and y. And I don't know what we would call this, but you know, this is some other function. And then somebody said opposite of an AND gate. So while our AND gate is 0, 0, 0, 1, what about 1, 1, 1, 0? That's what's called a NAND. And the way we write that is actually XY with a bar on top. And we could also do the opposite of an OR gate, which would be called a NOR. And that's x plus y with a bar on top. And it's just the opposite of this. So that would be a 1, 0, 0, 0. How many different functions could we make? I mean, we got 5 already.
Depends on how much information we're trying to decipher.
True, true. So in this case, we've got 2 input variables, and they're binary. Actually, turns out we can do 16 possible functions of 2 inputs. This includes some sort of possibly yes useful functions like the yes function, which just always says true, or the no function, which always says nope, false. All right, so somebody asked about the not operation. These are all functions of 2 variables, but we could define another variable like not x, something which just takes the value of x and just does the opposite. So if x is a 0, not x would be a 1. If x is a 1, not x would be a 0. And that's another function. So a total of 16 possible functions we could write. And not x is interesting because it doesn't care what y is. But it's still, something we can consider to be a function of x and y. So one of the punchlines here is when we're working with Boolean things with these binary values, the set of operations that we can apply to these is much smaller than with real numbers, and the operations are generally much simpler, and they're simple enough that they can be described with these simple tables. So these tables are called truth tables. And they're named truth tables because we think of these things 0 and 1 as being true or false, having a truth value, and it's literally a table of truth values. And so as we work with different ways to operate on variables, we can describe, if both of these are a 1, then the output should be a 1, otherwise it should be a 0. We can make descriptions like that in words, but we can also just write a truth table to describe exactly how some function operates on its inputs. And so when we start digging into, building circuits, which we're going to do in our labs, we're going to work with devices, integrated circuits that do logical operations on inputs, and we'll look at the data sheets. And you've done some of this in 120. The data sheet, a big part of it is usually a set of truth tables that tell you how inputs are transformed into outputs. And so some of the logical operations we'll work with a lot, and, or. The complement of these, the thing that does the opposite of these, which we call NAND and NOR. There's also an exclusive OR. And the way an exclusive OR works is almost like an OR gate, except for an exclusive OR to be true, we need to know that only one of A and B are true. So if A and B are both 1, we say the XOR is a 0. And so that's just a slightly different truth table from the plain old OR gate, where it was always 1 except when both inputs are 0. And we can have the opposite of this, which we call an exclusive NOR, so xnor, and that looks like this. Yeah, so this is also saying, do we have an odd number of inputs that are 1? Which ties into something called parity, which we'll talk about later, and we'll talk about in 270. And so it tells us, do we have an odd number of 1s, or do we have an odd number of 0s?
Excuse me?
Mm-hmm.
How would you be able to go through with the exclusive NOR? I'm just confused. Do you not the AND portion of it and then use exclusivity, or?
So this is do the exclusive OR and then just negate the result. So it's just exactly the opposite of whatever the XOR gives you.
All right, that makes sense.
Cool. If we didn't like that, though, is there some sort of intuitive way we can describe when the xnor is equal to 1, or when it's true? What is this thing actually telling us about the inputs when the output of xnor is a 1? Do we notice something about the inputs? Yeah, both inputs are the same. Up here the xnor can be a 1, down here the xnor can be a 1. Those are the only cases where our output is 1, and in both of those, A and B have the same value. And so an xnor is also an equivalence function. It says, do A and B have the same logic value? They're either both false or they're both true. So it's like an equivalence operation. So all of this stuff that we're talking about, all of these different operations, these different ways to combine Boolean things, where did that come from? When did that get developed? I mentioned it in passing a little while ago, but where does all of this come from in our history of technology and mathematics? Anybody remember or anybody know? Yeah, this is Boolean. What does Boolean come from? You know the name Boole? I think George. So this comes back from the 1850s. And George Boole was a mathematician who studied, among other things, mathematical systems involving two objects, which we can think of as 0 and 1. And he studied ways to combine these and properties of them, and you know, doing ands and ors and things like that. And so this led to Boolean algebra. So, you know, Clark, we do Math 110, Math 111, college algebra, right? 90 elementary algebra, and so on. Boolean algebra is a different version of algebra. The algebra we usually study in school, you know, says, you know, here's how you simplify an equation, here's how you manipulate polynomials, and so on. Those are usually concepts involving real numbers. Right, if you solve an equation in an algebra class and you're solving for x, x could end up being pretty much any real number. Negative 17.26. or positive 15, right? Boolean algebra, you're working with things that are ones and zeros. And so this was developed as a mathematical discipline, 170 some years ago. And it turns out to be really useful when you want to build computers and you want to do computer science. But the subject itself is a mathematical study. All right, so let's look at applications. So let's suppose we want to build a combination lock. So we've got something we want to protect, and we want to design a circuit so that you need to know the secret combination in order to open up this box. And I'm going to keep, my chocolate chip cookie recipe inside this box. And I don't want other people to find it. So I'm going to guard it with digital logic, right? So I want to build a combination lock circuit. Well, anytime I want to build a circuit in this course, right, or really, in general, or for that matter, anytime I want to write a program, if I'm a computer science person, I want to start with at least a mental image of the high-level view of the thing I'm trying to design. And so for this course, this is going to be what we call a system diagram. And system diagram, that's your 40,000 foot view of the problem. So what does my combination lock look like? I'm going to have some kind of box with some circuitry inside it. And I'm going to have a 3-digit combination. So I'm going to have 3 inputs, A, B, C. And I'm going to have an output, which I'm going to call unlock. Now we don't know yet what goes in here, but when I finish building this circuit, this is what this circuit's going to look like to somebody who wants to use it. You're going to have to come up with a way to feed 3 signals into it, A, B, and C. It's Boolean, it's binary, it's digital, so these will be 1s or 0s. And it's going to generate an output signal, which will also be a 1 or a 0, which says unlock the box. Now, A, B, C, those could come from push buttons. They could come from, toggle switches that I flip up or I flip down. They could come from, a touch panel where I have to touch, a certain area of an input panel to, say I'm pressing A and C, for example. But I'm not worried about that in this level of designing the system, right? All I'm worried about is I've got 3 inputs going in. And the unlock signal, well, that might, drive something called a solenoid, which pulls a bar out of the way of a latch so that the box can open up. Or it might activate a piston that automatically opens up the top of my box. Or, some other unlocking mechanism. But I'm not worried about how that unlock mechanism is going to work. Right? At this point, at the level of a system diagram, all I'm interested in is what goes in, what comes out. Well, to take this and start designing a circuit to implement it, I need to somehow take this idea of unlocking something and I need to say, how does that relate to 1s and 0s? And so I'm going to put in a key here which tells me what the value of these different inputs and outputs mean. And so I'm going to say unlock. 0 means my box will be locked. 1 means my box will be open. Now this was an arbitrary decision. I could have easily said I want 0 to be open and 1 to be locked. But I've got to know what the intent is for this circuit. So that if I go off and I buy, you know, a piston that's going to open up the top of my box when I want it to be unlocked, should I get a piston that you know, opens up when it gets a 1, or should I get a piston that opens up when it gets a 0? You can do it either way, but you've got to make a decision. Now, if I'm getting push buttons, you know, some buttons, when you push them, they generate a logic 1. Some buttons, when you push them, they generate a logic 0. The buttons we use in this class, they're mostly going to generate zeros when we push them. You can do it either way, but I need to know, for the sake of designing this system, what are the values of A, B, and C? What do the zeros and 1 means? So I'm going to say 0 equals not pushed. 1 equals pushed. So if I'm thinking of these as push buttons, I'm imagining if I don't touch the button, it's going to be generating a 0. If I touch the button, I'm going to be generating a 1. But I could do it the opposite way. I could say if I don't push the button, it's a 1. If I push it, it's a 0. Or if these are flip switches, I could say if I flip it up, it's a 1. If I flip it down, it's a 0. So here's my system diagram. It's this high-level view of what goes in, what comes out, and a detailed explanation of what the values of 0 and 1 mean for each input and each output. And you got to have all of those pieces to have a valid system diagram. And this is the first thing you're going to design anytime that you're designing a circuit. You're going to be doing a circuit design for Lab 1. We'll talk about that in a few minutes. So the very first thing you want is a system diagram. And it's sometimes called a black box diagram because we don't know what's inside this rectangle. So we picture it as, you know, a painted container you can't see inside. And we don't draw, you know, any equations in here or any circuit diagrams or logic diagrams or anything like that. It's just, you know, what goes in, what comes out. Once you have this, though, now you need to design the circuitry. What kinds of logic operations should I perform on A, B, and C in order to generate this unlock signal? So the next step after we've got a system diagram is going to be to come up with a truth table. So you've got a system that you're trying to build. How do you develop a truth table for it? And so this is still kind of rehash of ECS 120. This is like your plane landing system, but I want to make sure we develop this from scratch. So the first thing I'm going to do is say, well, since I have 3 inputs and they're binary, there are 8 possible situations. If the person is trying to unlock the box and they've, you know, pressed some combination of buttons or flipped some combination of switches, there are exactly 8 possibilities. It may be that none of the buttons are pressed. It may be that all of the buttons are pressed. It may be that some of the buttons are pressed and some are not. And we'll talk more later about, you know, how I knew to come up with exactly these 8 combinations. But if you think about, you know, the different ways that A, B, and C could be a 1 or a 0, you will eventually find 8 possibilities and no more than that. And so I've just listed these 8 possibilities in this left side of what's going to be a truth table. All right. So I usually want my box to be unlocked unless the person puts in the exact right secret combination. All right. And I'm really guarded about my chocolate chip cookie recipe. So I want to pick a good combination that nobody will ever think of. All right. So I'm going to choose 111 as my secret unlock code. Because that's so obvious nobody would ever think of it, right? So my box is going to be locked in all situations unless all three inputs are 1. Yeah, right? And in this case only, I want my box to unlock. All right. Well, there's my truth table for what goes inside this black box, this system diagram. And if I were to go ahead and build up, some circuitry that produced this output based on these values of the inputs, I could take that circuitry, I could put it inside here, connect A, B, and C, where they go to the inputs of my circuit, take the output and connect it to this arrow. And now I've got, my combination lock fully designed. So our next step after the truth table after the system diagram is going to be the truth table. All right, since we're here, and you're not going to need to go beyond this for lab 1, but since we're here anyway, let's just go a little bit further down this path, and then we'll switch to lab 1. If I wanted to write a Boolean equation for my unlock signal in terms of A, B, and C, any idea what this equation might look like? In terms of ands and ors and nots and XORs and things like that. So yeah, some people are saying this in chat. This is just a good old AND operation. Because I want to unlock my system when A is 1, and B is 1, and C is 1. And so this is just A and B and C. Well, it turns out that, just like there's an AND operation for 2 inputs, we can make a truth table for an AND operation of 3 inputs, and it looks exactly like this. So in addition to having picked a password that nobody would ever think of, I also picked a password which makes my circuit really super easy to design. Because I can find a physical piece of hardware called a 3-input AND gate, and if I put 3 1s into that gate, I'll get a 1 out, and every other time I'll get a 0 out. So if you happen to be lucky enough and you get a truth table like this, coming up with an equation for your output will be pretty simple. And our next step after a truth table will be to come up with an equation. And then from an equation we can come up with a circuit design, and then we can implement. And yeah, someone pointed out in chat, if we're implementing this, we could actually do this with 2 plain old 2-input AND gates. We could take A and B and take the result of that and AND it with C. So if you don't happen to have something that automatically does an AND of 3 inputs, we can still do this pretty easily. Alright, let's make our circuit a little more interesting. Suppose you have one friend who you really trust with your chocolate chip cookie recipe. And so you want to give them access to this box. But you don't want to give them this password, because this is also the password you use for all your other stuff in life. And you don't want to give this person, access to your Amazon login and so on and so forth. So you want to create a second password that will also unlock this. And let's just say, we're going to give this password for your friend. So I want 2 combinations that will unlock my box, my secret password, but also the secret password for my friend. And so I want a slightly different circuit which will unlock not only when all my inputs are 1, but if my inputs are a 0 and a 1 and a 1. Well, this is a little trickier, because we don't have a gate which says output a 1 when my first input is 0 and my second and third inputs are 1. We want the output to be true when this is a 1 and this is a 1, but also when this is a 0. So yeah, someone jumped ahead in chat, and you are correct, we could just do B and C. But let's suppose we don't have that insight. Let's be really kind of mechanical about this. And
A not B and C.
Say again?
A not B and C.
Yeah, so well, if we had, 1 1 1, we want this to be a 1, this to be a 1, this to be a 1, we can use an AND gate. Well, if all we have is an AND gate, we could rephrase this question as saying, yeah, we want A to be a 0, B to be a 1, C to be a 1. But if we think of what A bar is, in this case, not A is a 1. And so this is, again, an AND of 3 things, but the 3 things are A bar, right, not A, B, and C. And so we also want to unlock when A is a 0, and so A bar means not A, and B is a 1, and C is a 1. And so this should unlock, this should unlock. So the final unlock signal from our circuit should be true when this is true or when this is true. And so if we OR these together, there's our equation. Our unlock signal should be asserted when A and B and C is true, or A bar and B and C is true. And so there's a slightly more complex equation corresponding to this truth table. And so we'll go over next time probably a very methodical way to get this equation from this truth table without having to do all the talking that we just did. And this will somewhat be a review of 120 depending on how you learn this in 120. But we'll find a systematic way to write these equations from here. And that way is going to be something we call a sum of products, or an SOP. And we'll work with sum of products a lot, and that'll be the main thing we use in this course, but we'll also talk about a dual to that, which is called a product of sums, where we look at the zeros instead of the ones. And then we'll look at how can we simplify equations, because as someone pointed out in chat, this is actually the same thing as just B and C. The value of A doesn't matter. If B and C are both 1, it doesn't matter if A is a 0 or a 1, we want our output to be a 1. So we'll spend a fair amount of time looking at how to simplify an equation like this into something like that. And the main thing we'll talk about for that is something called a K-map, or a Carnot map. So these are all things we're going to get into in more detail down the road. This is just kind of a preview of coming attractions. But let's change track at this point. We've got about 40 minutes left in class. Let's go ahead and take a look at Lab 1, because Lab 1's due Friday, and so we want to get started on that. So the labs are all linked up in Canvas. And so here's your first lab, Lab 1. So since we're remote this quarter, the labs are done using simulation. And so we're going to use a system called tinkercad. And if you did 120, you probably work with Tinkercad in there. If you've done 101 with me, we use Tinkercad to do some 3D printing design. And so we're going to use it for ENGR250. If you do 270 remotely, you'll use may use Tinkercad in there, but mostly we use a different piece of software. So there's some videos you can click through to look at this, but I want to go through basic Tinkercad operations here in class. So let me talk about the experiments first, and then we'll play with some Tinkercad, and then I'll talk about lab reports. So the experiments, the first one is to play around with Tinkercad and basically look at the different types of things that you can put on your simulated protoboard. So protoboard, you know, it's the breadboard thing with a bunch of little holes in it that you can put components into to build circuits. So some of the things you can put in there: resistors, light emitting diodes, the protoboard itself, and then some test equipment, a power supply, multimeter for measuring voltage and current, a function generator for generating waveforms, and an oscilloscope for looking at waveforms. And so you want to mess around with these, build some circuits, see what they can do. A lot of these things have different things that you can change. If you have a resistor, you can say, how big is my resistor? Is it 1,000 ohms? Is it 10 ohms? Is it 1,000,000 ohms? If you have an LED, you can specify the color, for example. If you have a power supply, you can say how much voltage do we want, where does the positive and the negative go, and so on. So it's playing around with the equipment, and we'll hop into Tinkercad in a minute. Experiment 2 is looking at a protoboard and trying to figure out how things are connected. And Tinkercad makes it pretty easy because it highlights connected rows when you hover. But you know, from 120 you should know which of these holes are connected to which. And by understanding that connectivity, you can use these protoboards to build circuits by plugging components into the right holes, plugging wires into the right holes, and effectively connecting components together by just placing them in here. So experiment 2 asks you to do some experiments to figure out what the connectivity is, and then show the connectivity by drawing lines between the connected holes. So if these 5 holes are connected, I should draw a line between these. Alright, experiment 3 looks at 2 pieces of equipment, the function generator and the oscilloscope. Function generator creates waveforms, so you can use it, you know, to produce a signal that you know, might look like this. And an oscilloscope lets you take a waveform and see a representation of it visually. And these are pieces of equipment that, you know, physically exist in the lab, in the STEM building, that you would work with in person. So you might use these in 270. But we have simulated versions of these. So experiment 3, introduction to the square wave. So what is a square wave? Well, a square wave is what it sounds like. It goes up, it goes down, it goes up, it goes down. Maybe this is like a rectangle wave, but it's squarish. So that's a typical square wave. But even with, you know, a very basic waveform like this, there are a lot of parameters, a lot of aspects of this that can be changed. So one aspect is the frequency, 1 kilohertz. Frequency is how quickly does it go up and down. And hertz, sometimes called a cycle, abbreviated Hz, means something goes up and down once per second. And we use metric systems, so a kilohertz is 1,000 hertz. And so 1 kilohertz is 1,000 hertz equals 1,000 up-downs per second. So how quickly is it waggling? If you were to hook this up to a speaker, you would hear a tone. It's in the range of frequencies that humans can hear pretty easily. If you do this at 10,000 hertz, your 4-year-old can hear it, you may not be able to. If you do it at 20,000 hertz, probably you won't be able to hear it, but your dog might. So frequency is how quickly it's moving up and down. So we want to play with a 1,000 hertz signal. And then this notion of duty cycle, well, it might be going up and down 1,000 times per second, but you know, it could be doing something like this. It could be going up and staying up for a long time and then dropping down. And then going up, staying up for a long time, dropping down. Going up, staying up for a long time, dropping down. And so on. That's the same frequency, but it's on for a lot longer than it's off. It's still changing 1,000 times a second. But the duty cycle basically says how long is it on versus how long is it off, how long is it high versus low. So we want a 50% duty cycle. So this original thing, high, low, equal amounts of time. All right, and then the third thing is 5 volts peak to peak. So if we think of these as representing voltages, what's the difference in voltage from this level to that level? 5 volts. This is sometimes called the amplitude of the waveform, and we can change it so that, you know, maybe it's a total of 1 volt from peak to peak, and it's a very, you know, small waveform. Or we could make it, you know, 50 volts down to negative 50 volts, 100 volts difference from peak to peak. So for this experiment, we want to set a 5 volt peak to peak. And the last thing is a DC bias. Because a 5 volt peak to peak, well, it could look like this, or it could look like this. Exactly the same frequency, exactly the same amplitude, exactly the same duty cycle, but all the voltages have been shifted up by a little bit. Or, you know, here's another waveform. Exactly the same amplitude, the same frequency, the same duty cycle, but all my voltages have been shifted down by a certain amount. So that amount of offset, that's called the DC bias. And since we want 5 volts peak to peak with a DC bias of 2.5 volts, here's what your waveform should look like. Right, it should go from 0 to 5 volts. And this should waggle up and down 1,000 times per second, which means that the time from one upward transition to the next is going to be 1,000th of a second, which is also 1 millisecond. This is called the period. Frequency is 1,000 waggles per second. Period is 1 millisecond per up-down oscillation. Right, so we've got all these concepts. We've got duty cycle, bias, amplitude, period, and frequency. And they're all describing the behavior of this waveform, which translates to the appearance of it. So experiment 3 is just playing around with that. Right, so lots of knob settings that you can make on the function generator and on the oscilloscope, and take a look at what your waveform looks like this. So set the oscilloscope and the function generator accordingly. Okay, and then include the resulting diagram in your report. So draw a sketch, right? And show, you know, what your waveform looks like for those settings. And then do the same thing, but change the frequency to 20 hertz. And a 3 volt peak to peak with a bias of 0. And then set your frequency to 50 kilohertz, same duty cycle, 4 volt amplitude, and a DC bias of 2 volts. So this is just getting practice with thinking about these concepts. I'd like you to draw the pictures actually for this. Normally you could do a screenshot or something, but I want you to actually draw this and label it up by hand, because that just feels a little more real somehow. All right, and then experiment 4. So experiment 4 is going to be a traffic light controller. And this is an experiment we're going to come to in a number of labs, probably 4 labs I think total, will develop this traffic light control system. And so we're going to build it up. In lab 1, you're doing kind of the high level design of this system. So you're going to basically make a system diagram and a truth table for a traffic light controller. And so what does this look like? We've got a 3-way intersection, and we're going to draw it like this, and we're going to think of this as west, south, and east. All right, I'm going to put a note here. This is one of these things you get in lecture that you don't see in the lab right up itself. The layout of this intersection is critical. I'm going to insist that you lay out your intersection exactly like this. So a horizontal pathway and then one lane coming down to the bottom, labeled west, east, and south. Could you do this with your other road going up to the north instead of the south? Yes, but you will lose points for that. Okay? I'm being dogmatic for a reason. I'm usually not dogmatic. If I am, there's a reason for it. The reason is we're going to spend probably half of this course in one way, shape, or form developing this intersection. And if you decide you're going to call these A, B, C instead of west, south, and east, nothing that we do in class is going to line up with what you're doing. And when you're confused and your circuit's not working, in week 5, and you're looking at your equations are written in terms of A, B, and C, and our equations that we do in class are written in terms of W, S, and E, you're not going to be able to make sense out of what we're doing. So I'm going to absolutely insist that you draw your intersection like this, with one lane running from left to right and the third lane coming down to the bottom, and that you label these west, south, and east. And I guarantee this will make your life easier. Alright, so we have a 3-way intersection. Each direction has one lane controlled by one signal. So this is a really simplified intersection. We have a light here, a light here, and a light here. And we're not thinking of 2-way traffic going down the road. We're just thinking of one car can be on a section of road at a time. And we're going to govern this with the laws of the state of Washington, which means the car on the right has priority. So the car on the right has priority. And only one lane is green. So what does this mean? If there's a car sitting to the east, it gets a green light, everybody else is red. So east has the highest priority. If there's a car to the east, that car has a green light, everybody else has a red light. If there's a car to the south, and there's not a car to the east, then the car to the south has a green light. Nobody else has a green light. Everybody else is red. And if there's a car to the west only, no car in the south or the east, then west gets to go. So no yellow lights yet. The last version of this in Lab 6 will put in yellow lights. But for now, we're starting off with probably the simplest way we could envision a traffic light controller. So each lane has each direction has one lane and one signal control light, red or green. So identify the input variables and the output variables. Sketch the intersection. identify the values, and then draw a truth table. All right, so requirements for this experiment. Let me show you a system diagram. I'm giving away part of your lab. But here's what your system diagram looks like. West, south, and east. Those are your three inputs. These are your sensors which tell you, is there a car sitting on any of these lanes? 6 outputs. Each lane has a red light and a green light. And so I'm going to call these red west, green west, red south, green south, red east, green east. All right. 3 inputs, 6 outputs. This is important. Okay, this will get you maximum points on the lab. So for these sensors, 1 means there's a car present. 0 means there's no car. For these outputs, 1 means the light is on, 0 means the light is off. Alright, this is the system diagram you have to use. Could you implement a traffic controller differently? Yes. Could you implement a controller where a 0 means that there's a car and a 1 means there's no car? Yes. But do it like this. Okay, this is not written up in the lab. I'm telling you this now. We've got all 20 people in class, so there should be no confusion or ambiguity about this. All right. So it's got to have 3 inputs, 6 outputs. And this is one of these things, if you talk to people in other sections, if you go online, if you search around, you'll see implementations of this that only have 3 outputs, where 1 means the light is green and a 0 means the light is red, right? You lose points for that. I want 3 inputs, 6 outputs. Ultimately, this is what you're going to have to do anyway. We're going to do this from the beginning. All right. So what should you do for experiment 4? Draw a picture of the intersection, right, like we did already. Draw your system diagram, and you know, specify somehow near your system diagram what the 1s and 0s mean for the inputs and the outputs. And then make a truth table. And design your truth table based on these priorities. Anytime there's a car to the east light should be green, all the other lights should be red. If there's a car to the south and nobody to the east, then south should be green, everything else should be red. And if there's a car to the west only, no car on the east or south, then west should be green, everything else should be red. If there are no cars present, I don't care which light is green, I don't care if they're all red. You can do whatever you like. But whatever you do, there should never be more than 1 green light at a time. If there's some combination of cars where you have 2 green lights, you're going to have collisions. Right, so only 1 lane is green. And for the case where there's no cars anywhere, you can choose what you want to do. All right, and you take this design as far as developing the truth table. So you don't have to design an equation, you don't have to build a circuit, you don't have to do anything in tinkercad. Right, it's just developing it up through the truth table stage. All right, questions on any of that?
Yes.
Yeah.
So, with the truth table and all that, would you want it hand-drawn, or do you want us to, I don't know, do it using digital and screen capture?
So let's talk about lab reports. And general guideline, right, is it should be neat and legible. My suggestion is for everything except figures, for everything except something like this, type it up, right? Do it digitally. You don't have to actually make a table if you use a font that has fixed spacing like Courier or some monospaced font. You can just type in a truth table by putting spaces in between the ones and zeros and so on. But I want you to think of your lab reports as being extremely professional, right? I want you to think of these as something more than just, class starts in 10 minutes, I've got to finish writing down my answers, right? I want you to think of this as something that you would, present to a room full of people at some lecture symposium, and they'd be looking at this and following along. So you can draw pictures like this or your traffic intersection as long as you draw it neatly. Everything else I'd like to see typed. All right.
Opposed to templates for the report structures.
What do you mean by templates?
Like if I've drawn up a template from previous labs that has it kind of like organized.
Yeah, that's a good strategy. Because most of these are going to be the same, right? The details will change, but here's a suggestion for organization, right? And I'm okay if you change some of the wording of this and so on and so forth. But I'd like your reports to look like the following. So I want a cover page, which basically says, Engineering 250, the lab number, your full name, first name, last name, right? That's important. Don't just use initials. If you were working with lab partners, you would list your lab partners, but labs are done individually in this section. And that's all that goes on the cover page. It's a title page, right? And then a section called Introduction, and I absolutely want an introduction. This can be one sentence, but I don't want to turn the cover page and start seeing Experiment 1 if I don't know what this lab is about. From the cover page, all I know is this is Lab 1, right? So make, a one-sentence introduction that says, in this lab we work with tinkercad to get familiar with the equipment, and we design a traffic control system. That's a great introduction, right? It's like a textbook. You open up a textbook, you don't just start seeing calculus questions, right? You see, oh, calculus is a wonderful subject that was developed blah, blah, blah years ago, right? There's an introduction to this thing that you're holding that you're about to read. So put some kind of introduction in your report. Do it in your own words, though. Don't just copy and paste, right? And then go ahead through your experiments. So for each experiment, you don't have to call it objective theory, observations, etc. But for each experiment, I want to know basically what you're doing in the experiment. Whatever calculations you have to do, whatever work you have to do for the experiment, put that in your lab report, right? How you went about doing the experiment. Well, first I took this circuit and I built it on a proto board and I connected 5 volts to it, and then I used a multimeter to measure the output at this point. Put that in your write-up, right? And what happened when you did that? Well, a little bit of smoke came out of the middle and people ran out of the room screaming, and I realized that the voltage was hooked up backwards. Put that in your lab report, right? Results, discussions, anything that the experiment asks you to do, put that in your lab report. And then go on and do the same thing for experiment 2 and experiment 3 and so on. And the overarching goal here is that your lab report should completely explain what you're doing. Don't think of it as homework, where I'm just looking for the answers written down. I want to be able to take this lab report and hand it to somebody who has never done this course, and they should be able to reproduce your work. Okay, this is how science works. You do experiments, you document them, and then somebody else can take your documentation and reproduce the experiment you did and see if they get the same results. right? So this is the most important thing. Lab reports should be standalone documents that fully explain to the reader what you did, why you did it, how you did it, what you observed, what you concluded, and so on. All right, and that's going to be the biggest thing where people get a lot of feedback from me saying, you know, you didn't put in a circuit diagram, how do I know what you did? All right, you can read through the general guidelines, but basically make things neat. You're going to upload it as a PDF, so it'll mostly be computer generated. Make sure everything is in your own words. If you copy anything verbatim, a figure, a set of words, more than 5 words in a row, you got to cite it. Right? If you copy something from the lab assignment as to what it is that you're doing this experiment and it's word for word, you got to put a footnote there and then put references at the end and say this was taken from such and such, and cite your sources. We'll go through this more on Wednesday, but you should be able to get through most of the lab itself after today. And then we'll talk about new experiments next time, but I want a new experiment section at the end of each. So read through this and we'll talk about that in detail. Let's hop into tinkercad really quickly and spend the last 10 minutes just getting that up to speed. So tinkercad, if you haven't done this, right, go to tinkercad.com, sign up for an account. Spell it correctly. And I'm just going to sign in through Google. So do a personal account, and you can sign in however you like. But first time you do this, it'll take you through some tutorials. You can skip the tutorials. Just go over here to circuits and create a new circuit. And it's all drag and drop, right? This is designed to be mostly intuitive. So I can scroll down and I can take a breadboard or a protoboard and drop it in here. And I can take an LED and drop it over here and put a resistor here and maybe put a battery in here. We'll do a big old battery. And so I can build some wires by just clicking and dragging. I'm not even using my protoboard right now. This might blow up my LED because it's only supposed to take about 5 volts. But I can build a circuit like this and I can say start simulation and hey, my LED turned on. And if I click on this resistor, I can change the resistance. It's 1 kilo ohm. What if I make it 1 ohm instead and I run my simulation? Well, my LED just blew up because I put too much current through it. Right, so think back to 120. When you use a LED, you have to put a resistor in series with it to limit the current. We'll be talking about that more in the coming classes. But you know, you can place these components in the protoboard and make connectivity. Once you discover the connectivity, and again, there's a little cheat. If I hover over one of these circles, Tinkercad will show me which circles are connected to it. So experiment 2 is kind of done for you by Tinkercad. Alright, we don't have to design anything in experiment in lab 1, we just have to work with the test equipment. So under basic components, if you go to all, you can scroll through many more options, including the power supply, a multimeter, a function generator, and an oscilloscope. And for each of these, if you click on it, you can see different settings that you can make. And so these will help you answer those other questions in the lab. And so you can hook these together. I could take my function generator output and I could feed it into my oscilloscope. You can do this a lot more neatly than I'm doing it right now, but we're running out of time. But if I start this simulation, hey, I've got a waveform on here, and depending on you know, what I do to the frequency. I can change how my oscilloscope displays things. So if I'm displaying 1 millisecond per time division, that's from line to line here, and I've got a 2.22 kilohertz signal, this is what it looks like. If I bring the frequency down, my waveform gets spread out more. Here I can change the amplitude. Here I can change the offset. I can change it from a square wave to a sine wave to a sawtooth wave, and so on. So for this lab, you don't need to use a protoboard. For the other labs, you're definitely going to need to use a protoboard or a breadboard. But for this one, where you're just hooking up the function generator to the oscilloscope, you don't need to get the breadboard involved. All right, so I'm pretty sure most people have used this software already in 120. It's fairly self-explanatory, but go ahead and jump into that. Start working on the lab. I have office hours tomorrow morning. I've got, I think, an hour and a half of office hours in the morning. I'll have hours Wednesday afternoon, and then Thursday morning and Friday morning. But work on this now. Bring questions to class on Wednesday, or bring them to office hours tomorrow. And have fun with it. Tinkercad is fun. You never burn your fingers on it, unlike the real lab, and it's pretty intuitive once you get into it and you get through the basics. All right, we are out of time. That was a fast hour and 50 minutes for me, at least. Let me know if you have any questions. Otherwise, I'll see everybody next time. Have a great rest of your day, too. Thanks.
Bye, everyone. Thank you.
Thank you.
All right.
Thank you.
You're welcome. Catch you all later.